Alrighty, in this Marshmallowium lab, we are going to look at the different isotopes of our fictitious element Marshmallowium. An isotope is a different atom that has the same number of protons but has different number of neutrons. Since we can't see our elements, we're going to represent them with marshmallowium. Okay? And those isotopes of our elements will have different numbers of neutrons, which means that they have different masses. And that is the same thing for our marshmallowium. In our elements, we have carbon having 3 isotopes as our biggest, most common example of this. There's a carbon 12, 13, and 14, and they differ by the number of neutrons. So carbon 12 has a mass of 12, carbon 13 has a mass of 13, carbon 14 has a mass of 14. Okay, they each have 6 protons, but they have different numbers of neutrons. Okay, carbon 12 has 6 neutrons, 13 has 7 neutrons, and 14 has 8 neutrons. And those 2 extra neutrons make it that much heavier. So when it comes to looking at our different elements, you'll see that they have these different symbols in the upper left-hand corner. That refers to their mass number. And the mass number is the number of protons and neutrons in that atom. Well, if I were to take an average mass, I would have to take the mass of carbon 12, 13, and 14 and add them together. So an average mass would be 12 plus 13 plus 14, and then we would divide by 3. That gives us 39 divided by 3 with an average mass of 13. Okay, so let's check our periodic table. Our periodic table will tell us how much the mass is. Well, in the periodic table, it says 12.011. What? 13 is not the same as 12.011. So what's going on there? The reason why the mass isn't the same is because the mass that goes on your periodic table is a weighted average mass of all of the atoms that naturally occur in that sample. Carbon 12 is the most common of all of the carbon types, all of the carbon isotopes. Carbon 13 is only 1% abundant. Abundant means how common it is. So how often you see it occur in nature. And carbon 14 is really, really rare, less than, hundredths, thousandths percent. All right, most of the carbon in all of the world is going to be carbon 12. So the average mass, the average atomic mass, has to reflect that. So that's 12.011. Notice how that is closest to the one with the biggest percentage. Okay, you can't take a straight arithmetic mean, a straight average, where you take those numbers and add them up, then divide by 3, okay, because that would be 13, and that wouldn't be an accurate representation. So what we're going to do is we're going to use a special equation to figure out what the atomic mass is. Okay, so the atomic mass is figured out by taking the relative abundance, which is the decimal form of the percent abundance, and we're going to multiply it by that mass number. Okay, so this is how much it weighs. And then we repeat that for however many isotopes exist for that element. Some elements have 2 isotopes, some have 3, some have 6, some have 4. All right, but the big thing is knowing which one, relatively speaking, is going to have the greatest abundance. So if 67% of your sample is going to be one of the isotopes, the same thing will be true for the relative abundance. The percent abundance is out of 100. The relative abundance is out of 1. It is the decimal form of that substance. Okay, so in this lab, Marshmallowium, we have our sample. Okay, there are 100 marshmallows in here. Marshmallows. Okay, there are 4 different isotopes. There is the jumbo, there is the large, there is the mini, and this little itty bitty person is the micro. Okay, this is what is freeze dried, and it is really, really, really light in mass. So we have to figure out where and how many of each of our different types are in here because they each have different masses and they have different percentages. So they will all add up to 100. Okay, so when you go through this lab, you will see that you are going to have some different pictures. So you can count how many of each type you have. These are groups of 5. These are also groups of 5. And the singles are down here at the bottom so that you can count what your percent abundance will be. And I'll show you pictures of how much their mass is on the scale, and we'll be able to figure out the weighted average. A weighted average depends on how many there are. Just by looking at this picture right here, which one does it look like there's more of? Yeah, there's more minis than anything else. So that means our mass should be closely reflected to the average mass of a mini marshmallow. Okay, next would probably be our micros, then our large, and our rarest is going to be our jumbo. So that is our Marshmallowium lab.